Welcome everyone to the PyTorch technical deep dive and what we call the core maintainers keynote. So I'm Alban. I'm one of the core maintainers of PyTorch. And so today we're going to go through a few of the highlights and things that have been happening with a few people from the core team. So first of all, PyTorch is turning 9 this year, which has been an amazing journey. We've witnessed we managed to witness yet another AI revolution, which is amazing. We can now generate these amazing images, which is nice. But you wouldn't believe how much time it took to actually get 9 candles on that cake. And we gave up trying to get them all on the same line because it was just too much work. So it's a good news. We have more to do. We will be able to continue, hopefully, for a few more years. So I'm going to do the first part of the talk here, which is going to be the state of PyTorch or something like that we've been doing for a few years. So we collected some stats on what has been happening, as usual. All the stats I have here are what I'm going to call conference years. It started and ended in August, so that we have nicely rounded numbers. And so for the first one, I want to start with our traditional audience, which are researchers. And so we're thrilled to see that most of the top AI papers being published are still using PyTorch this year, with more than 16,000 papers published in a single year. It's amazing to see, and I want to say a big thank you for keep trusting us to run all your workloads and all of that. It's amazing. And so all of this is built on top of a lot of the main PyTorch code base. So these are some stats on the main repo, actually. So the number of stars and forks keep growing so fast and very steadily over the years. So it's very nice to see that we continue to have a very nice momentum. There's still more and more happening in the community. And a lot of this leads to a lot of contributions. And the number of contributions just keeps growing. And so these bars is not cumulative. It's like every year there's more and more code being landed in the code base. Just last year, we got 14,000 commits, which is 50 to 100 commits a day, which is kind of insane, the amount of work it is to handle all of that. And you can see here an interesting bump in 2024, which is when we deleted Cafe 2 from the code base. And more interestingly, all of this work is done by more and more contributors. And that is very exciting to see that the number of people that contribute to PyTorch is also growing, with more than 1,000 people that contributed to the code base in the last 12 months. So another big thank you. I'm sure a lot of people here have sent GitHub PRs and contributions to the code base. Thank you very much for spending the time, working with us, collaborating, and helping us do something better together. On top of that, of course, the other, half of this room is building stuff on top of PyTorch. And it's been amazing to see how PyTorch has been able to enable so many projects. So we did some math on GitHub. There is more than 400,000 new projects that use PyTorch that were added to GitHub over the past 12 months. And that growth is insane in terms of new things happening all the time. Switching gear a little bit, I wanted to talk about 2 quick features that we've been happening, just to continue on the fun number side. One of them is Torch Compile that was announced 2 years ago here at the conference. And it's been very interesting to see that over the last year, the number of users have actually doubled. And more high-profile projects are now using Torch Compile. And it's great to see that the community is using that to make everything faster. The other one that is very interesting is dtensor. And dtensor is a new paradigm to do distributed and express how you write your distributed workloads in PyTorch. And what has been amazing to see is over the past year, we've been on 10x jump, which is very surprising, but it's great to see how people in the community use all the new features, all the new paradigms that we are developing. Similarly, Torch Titan has been a very interesting project built by the Meta PyTorch team, and the number of stars has been growing up significantly. including after the PyTorch conference last year. And we see the number of forks growing more and more and faster. Why are we thinking about forks here is because Torch Titan is a project that we want you to fork and use on your hand and tune for a specific cluster and workload to do larger scale training. And over the year, and this year, they actually added a lot of new models, including Qwen, DeepSeek, GPT-OSS, and all the new parallelism that you've heard already way too much, but context, expert, pipeline, all of these things. Very exciting to see. Similarly, in terms of other projects, we are working with the community and other projects outside of Meta PyTorch, which, for example, Transformer. So the Transformers project from Hugging Face has also been growing very fast. And it's been amazing to see how many new projects are coming up on GitHub that use PyTorch and Transformer jointly to build new things faster than what you would be able to do with only PyTorch core. A couple interesting new features that they developed this year includes kernels, which allow you to have your custom kernels directly in the model and distribute it through the hub, tensor parallelism, and the brand new attention interface that they built to be able to express more and more of the new attention techniques we need and the new transformer techniques we need. And of course, the two other projects that I'm going to go over that you've heard a lot about already are the two platform projects from the foundation that were announced last year. First with VLLM, that has more than 8,000 projects built on top of it, which is very interesting because VLLM is an inference engine. You don't expect it's going to be built into a new project, but reinforcement learning is now happening more and more, and VLLM is getting included in so many of these new projects. And finally, DeepSpeed, who also has been seeing a very big growth, and it's been amazing to see all this new technology being added there. And now to go from what has been happening to the new trends, I'm happy to introduce on stage Edward Yang and other core maintainers of PyTorch.
Thank you, Alban. So my name is Edward. I'm a core maintainer on the PyTorch project. And today I want to tell you about what we've been up to in PyTorch and where we're going in the near future. But before I can get into that, I have to kind of talk about, what happened this year in AI, right? And so I was preparing this slide and I was like, okay, what happened this year? Oh my God, DeepSeek R1 was this January. It's been an insane year for things happening in AI, right? DeepSeek showed us that, mixture of experts was now the architecture that all of the state-of-the-art models were going to be using. It also showed us that reinforcement learning was a really important component of what we actually wanted to do. So what we saw was people, instead of talking about how they wanted to keep scaling up pre-training, now everyone wants to do post-training and inference. And wow, this was a really big shift, especially for us on the framework side. Separately from that, I would say this year was also the rise of AI agents, especially in coding. They're not perfect, but they are certainly useful enough to actually materially impact how we do software development today. And beyond that, people are increasingly interested in hardware optionality, the ability to bring their own hardware to what they are doing for training and inference. There were many high-profile multimodal model releases, including in the image modality as well as the video modality, and people are still very interested in how to actually go ahead and run their models on edge machines like your phone or your laptops. So when I think about all these things that happen, what are some themes from this situation? Two really stand out for me. One is that, there has been a lot of attention on the numerics of the computation we're doing in our deep learning network. So for example, Anthropic had a very major service degradation incident where the quality of the responses was just not very good. And why was that the case? Well, it turned out there was a bug in their deep learning compiler, and that was what was causing, a really bad response quality in a lot of situations. situations. Or take for another example this blog post from Thinking Machines, which also made a splash. When you're doing reinforcement learning, one of the important things is you need to make sure the model you're training on is the same model you're doing inference on when you're doing the rollouts in reinforcement learning. And it turned out that for the most part, people were unable to get these two to line up the same way. And Thinking Machines showed us that, hey, there's this thing called batch invariance, which is important to think about if you actually want your RL to be on policy. Separately from that, we noticed that when it came to what people wanted to do when they were training their models, they wanted to go at a larger scale with more complicated parallelisms, and this was just giving us more and more grief in this sense. And so to sort of think about what this looks like, let's just take a look at what the modern stack looks like when you want to do post-training reinforcement learning, right? You have everything under one roof. You have training, you have inference, you have the evaluation environments that you're running the agent actions in to actually go about doing them. And all of these potentially need to be orchestrated differently. And so the lesson we sort of learn from this is, hey, people are actually asking a lot out of their frameworks. They're asking for much more control out of their frameworks than ever before. So let's talk about what we've been up to. So one, we announced Monarch. Monarch is a new distributed execution engine that's purpose-built for this new world order of reinforcement learning, right? The idea is that you can control your orchestration from a single process, a single controller, if you may, and then use that to control everything that is going on in your cluster. So there's a talk tomorrow at 12:15 p.m. on Monarch, and at 3:50 p.m. today, we're also going to talk about Torch Forge, a reinforcement learning framework that we built on top of Monarch. When we think about also what is going on inside of the various training and inference orchestration in this domain, we also find that we have more and more capabilities that we need to give to people. We need to be able to scale to hundreds of thousands of GPUs. People are very interested in using their communications libraries on different backends, not only NVIDIA GPUs, but also AMD and Glue. And we also find people are increasingly writing custom kernels that have distributed communication built into them. And there needs to be a flexible way of expressing what you want to do at the kernel level. So we've built these in the form of the Torch comms library and symmetric memory, and we've proven scalability on them with Meta's internal workloads. So the symmetric memory talk has already happened, sorry, but we're also going to be talking about PyTorch distributed and fault tolerance at 11:35 a.m. tomorrow, so look forward to it. Now I want to look a little bit higher on the stack and talk about what's going on at the more front-end user level. And the thing that we have been working on is about bringing back control to the user without giving up the performance that we have given to people in the form of the compiler. So to do some history, in 2016 we announced PyTorch, and we said, hey, PyTorch is an eager mode framework. When you want to do PyTorch programs, it's just like any other library. You call an operation, it happens. You have complete control about how you want to put your application together. And people really liked this. 2 years ago, we announced the PyTorch 2 compiler, and we said, hey, if you use torch.compile, we will give you performance for very little work. The advertisement was that you didn't want to work too hard, and we would give you more performance back. And as a result, you had to give up some control over what exactly happens in your program. And so today, we are bringing back control to the user. And the way we are making this possible is by taking our compiler and turning it into a toolkit of various pieces that you can pick and choose for what you want. So what exactly does that mean? That means we have a full export API that works for training, that you can go and do automatic differentiation with to get your forwards and backwards graph. It works with abstractions like D-tensor and collectives, and all of the intermediate representations implementations you get are in Python, the language you know and love, so that it's easy for you to hack and iterate in this case. Now, this discussion is a little abstract because, compiler toolkit sounds good, but what am I going to use it for? And so in the next part of my talk, I want to talk about some of the ways of using it. And so some of these are more experimental, some of them are more real, but they're all there to give you an idea about what you might be able to do with the compiler as a toolkit. So the first one relates to numerics, okay? So you care about numerics, you are a little suspicious about compilers, you want a way to sort of say, well, if I compile everything with Inductor, I might not know exactly where any given problem comes from. So I want to only compile specific regions, and those are the ones that I want to go ahead and, like I say, well, this is where I find something useful in this case. You want to do it incrementally so you can figure out what the change is. So what can we do? Well, a compiler toolkit might give you, and in fact it does give you, a way of annotating various nodes in your graph to say, hey, these are the ones I want to compile, and then we only apply Inductor on those regions and leave your other pieces the way they were as well. And so we built a generic annotations mechanism, and then we just have a special compiler which is able to pick out the pieces that should be compiled with Inductor. Now you might be wondering, hey, couldn't I have just done this by doing torch compile on individual pieces of my model? And the answer is yes, and this works, and we also wanted this to be possible. But if you do it in this way, you can still capture the entire graph. And I'm going to tell you, you really want the entire graph because it lets you do things like this. So earlier this year, we announced a system called Simple FSDP. There's a very nice white paper about it that I encourage you to read. The concept behind Simple FSDP is, why is it difficult to write a good implementation of FSDP? Well, the problem is that you have to make sure you start doing the collectives to gather your parameters early enough so that they show up in time for when you want to do the compute. And this means you need to do some sort of global scheduling where you move things to a spot where maybe it has no business being when you're writing a normal program. So the idea behind Simple FSDP is, hey, let's write a very, very simple implementation of FSDP. We'll use D-tensors to represent the sharding of parameters on your nodes. We'll use parameterization to automatically trigger the gather when you try to use parameters. And we'll use activation checkpointing to make sure we don't hold on to these fully gathered parameters in backwards. And as a result, this is very easy to trace with the compiler. You get a program that has both your code as well as the collectives that were implied by the use of D-tensor. And then you use a compiler to bring back performance by doing bucketing and reordering to get things you want. And so this would be very difficult to do in an eager-only setting, but with a compiler, you can just move things around the way you want. So we have an implementation of this in Torch Titan. In the paper, we wrote some optimization passes that were very specific to FSDP, and we've been working quite hard on a more generic optimization that works in a lot of situations. But you don't have to wait for us. You can also just write your own graph pass that moves the collectives where you want them to be. Now let me do something even more experimental to show off some more capabilities of the compiler toolkit. So the pitch for auto parallel is, hey, maybe you have a program and it's in some weird new architecture, so you don't exactly know what the best way to parallelize it. Could I ask my compiler to go ahead and make decisions for me about how to shard my parameters, how to shard the intermediates, and then get something that's good enough to start scaling with before I spend a lot of time trying to figure things out? So how can you do this with the compiler toolkit? Well, write your program as a single node program, do a graph capture to get the program, generate an ILP constraint that says, hey, well, these are all the choices that I could make for intermediate shards, and here's what the cost would be. You don't have to do it this way. You can do anything you like, and then solve that program, and then modify your program to insert all the collectives implied by this. And then you can go ahead and finish compilation, bringing back a new program that is different from the original program because you've also decided to change how your parameters are sharded. This is not something we can do as a torch compile pass. We're changing the semantics of your program. But with a compiler toolkit, you have all the primitives you need to actually go about doing this. We don't have a talk, but we do have a poster. Come see us at the poster session if you're interested in this. And so I mostly talked about training, but I want to talk about inference. So I'd like to welcome to the stage Peng Wu.
Thanks, Ed. My name is Peng Wu. I'm the engineering manager supporting the PyTorch compiler team from Meta. So industry trend-wise, on the inference side, we actually see a lot of similar things are happening, as Ed has mentioned. There is increasing demand to support heterogeneous hardware, perhaps more so on the inference side than training, simply because there are more hardware vendors and accelerators that are playing in this space. On distributed, we see the foundational models are becoming so big that the smaller configurations cannot fit on a single GPU, and the bigger configurations often requires multi-node setup, even after advanced quantization. Yes, and numerics and determinism, and I'm sharing another blog post from SGLand that talks about deterministic inference and reproducible RL training. We also start to see consolidation happening around the LLM inference serving platform. As Alban has mentioned, over the last 2 years, VLM has enjoyed tremendous growth in terms of adoption and ecosystem expansion. So that includes not only open source community, but cloud service provider, hardware vendors, and also big internal production system, including Meta's. So that makes VLM a perfect case study for us to illustrate how we are co-developing and deploying core advanced PyTorch technologies to help serving this fastest growing segment of server-side inference. So early this year, VLM announced a major upgrade of their core infrastructure, the V1 engine. And along this announcement, Torch Compile actually becomes a load-bearing part of the VLM LM inference pipeline. So the benchmark shows that with Torch Compile, we're able to bring between 5% to 90% performance improvements on some of the most recent models. And this is on top of the 30% performance improvements from piecewise CUDA-graph, which is also built on top of the graph capture mechanism of Torch Compile. So today, the majority of the 107 text generation LLM models use Torch Compile. Why? So actually for VLM, compiler serves as a high leverage point of control to enable applying LLM-specific custom optimizations to apply sound CUDA-graph and to enable compiler automatic fusion to many models across many different hardware platforms in a way without messing up with their model code. So I want to point out the emphasis here of enabling custom optimizations, because that's the theme that I'm going to come back to almost on every slide here. And this is a very unique way of using Compile. To give you, because of that requirement, one thing interesting about the VLM compile usage is it's not using stock Torch compile. So if you look at the VLM repo, you find this directory called compilation. And in there, there is a lot of customization about this VLM compile integration. It includes dozens of files of custom inductor passes for custom fusion. and it includes special customization on the compilation workflow to enable piecewise crudograph, versioning for dynamic batch sizes, and also caching compiled artifacts. So to give you an example, this chart shows you a typical workflow of compiling a VLM model, and every place when there is a text label, this is where the compiler is injecting some customization that's moving away from the stock Torch compile experience. So over the last 12 months, the PyTorch core team has worked very closely with the VLM team in hardening this VLM compiler by bringing new features into the PyTorch compiler core. So to give you some examples, we have improved the pattern matcher to enable more powerful custom fusion. We have added expansion points, blessed extension points to better control compilation workflow. So that includes how to control the guards, how to control the recompilation behavior, how to control graph splitting and dynamic shape specialization. We also shipped new deployment capabilities, such as compile caching to remove warm compilation time. And right now, we're working on a new feature called AOT pre-compilation that would completely eliminate compilation from serving time. And finally, we have added better support for custom ops. And if you want to learn more, come to Richard's talk tomorrow afternoon. But on the last point, I actually want to give you a concrete example. So the built-in crudograph support from Torch compile before actually is all or nothing effort. So if there's a single operator in the graph is non-crudographable, in the previous version of crudograph support from Torch compile, we just give up crudographing the entire graph. Unfortunately, there is a very important custom attention layer implementation in LLM models that is not crudographable. So this actually inspired the very customized implementation of piecewise crudograph. So today, with the 2.9 release, we're introducing a new feature called flexible crudograph, where the feature is inspired by the VLM compiler, and we standardize the interfaces so that there is a way for users to register operators as non-crudographable, and you can also register a special crudograph custom wrapper, and then the compiler would automatically split the graph into the crudographable portion and the non-crudographable portion. And the compiler can even reorder operators so that we can create a very large crudograph portion. So this feature is out there, and we're working with the VLM community to integrate this into VLM so that we can maintain this core feature, not only just for VLM, but for any general users. All right, so there is a poster if you're interested. As I said, I cannot talk enough about custom operators, so let me just geek out to mention two more things that's in the working. One is stable API. So this feature allows one to build C++ or CUDA ops and to be able to run it across multiple PyTorch versions. As you may know, that custom ops are great, but they are also potential technical debts for future releases. So with this feature, at least for the release engineer, they will save a lot of trouble. The second feature is called custom operator auto-tuning. So this one allows one to use the inductor auto-tuning system to auto-tune both custom implementation and then compiler-generated implementation. So this allows users to get the best of both and future-proof any future compiler improvements. All right, so let's pop back up. What's the high-level messaging? When we look back, actually, the VLM compile journey actually reveals very interesting design point for Torch compile, which honestly we didn't consider seriously before. So from the very beginning of the 2.0 announcement, our North Star for Torch compile has always been to push for this simple API to as many users as possible and save them from optimizing their models by hand. And for most users, that's exactly what they want. However, for a very small percentage of users, they actually want to use the compiler to enable them to build new powerful optimizations that they cannot easily express using PyTorch eager. So these users are frontier users because they are at the frontier of new model optimization or deploying new model architectures onto new hardware. And they cannot afford to wait for the compiler to catch up and deliver the optimization for them. So despite their small numbers, their work is highly leveraged and oftentimes trend-setting, especially when this field is still fast innovating. So the question is, what can we do to support frontier users better? Enter a new chapter of PT2. So here, we're going to offer 2 sets of compiler products. So there is the stock TorchOut compile experience that's suitable for most users. And then there is a second set of custom Torch compilers that's built on top of what Ed called as the compiler toolkits. And how do we get from one side to the other side? Actually, we're doing a lot of restructuring of the PyTorch compiler core to remove a lot of the hot wiring that assumes the implicit stock TorchOut compile workflow, and also to expose new capabilities to enable this new kind of compiler to be built. So to recap some of the concrete projects we're working on that Ed already mentioned, so we're working on a compiler deterministic mode. We're working on finer grain control on inductor. This is the inductor on demand project idea. So ranging from full-blown inductor everywhere with max auto tune to the minimalistic inductor where we only support custom optimizations and everything in between. And the third project is about the graph capture capability. So we're working on to enable the ability to capture a full joint graph with both backward and forward. And this is essential for frontier users to build custom distributed compiler that would be able to do global communication optimizations. So with that, and with us sitting literally next to the frontier users, either on the inference side, on the training side, and we hope we're delivering a more powerful P2 experience that would enable more and more powerful custom P2 compilers out there. So with that, I'm going to pass the mic to Mark, who is going to talk about bringing PyTorch to anywhere and everywhere.
Hello everyone. My name is Mark Saroufim. I'm an engineer on the PyTorch team at Meta, and I'm also the co-founder of a large ML systems community called GP Mode. Today I want to talk to you about how you can make PyTorch run anywhere. So really our vision for this here has been we want PyTorch to run anywhere on any device that you want, on any software backend that you want. I'll define what that means in a second. And you can modify whatever you want. So we've heard our users say that PyTorch debuggability and understandability has been suffering. And so this situation is mid, and we understood the assignment, right? And so the first thing that we did was we wanted to make it easier to have non-CUDA devices be more first class. And so we introduced this new namespace called torch.accelerator. So this namespace will support things like a device, streams, context. And so now you don't need to have these awkward if conditions depending on accelerator. You can just have the 2 accelerator and it'll just send things to the right device. You can also create your own device. And what I mean by this is if one of those accelerator isn't necessarily in core, we have this new infrastructure called private use 1 where developers can come in and define their own memory allocators, their own streaming behavior, their own event behavior. And this code doesn't even need to be in core. So basically anyone can have this in core experience without the permission of a core maintainer in PyTorch. The second thing, which is a bit different, it's a change from how we historically defined a backend, which also includes software backends. So for instance, let's say you really like the PyTorch front end because most models on Hugging Face are in PyTorch, but you really want the kernels from TinyGrad. Great, you can just say to tiny device, and you'll dispatch to the tiny kernels. The way this works is like very simple. You can almost think of it like sort of a, because like Python is an like, interesting language. You can monkey patch everything. So here, for example, on the left-hand side, you have like all the PyTorch ops. And on the right-hand side, you have like the custom kernel implementations you might have for those ops. So like this could be like tinygrad code, it could be like Jax code, it could be Qt code, Trident code, doesn't really matter. So you get like this really nice like monkey patch experience, and it works for forward passes because they're ops, like a composition of ops. Works for backwards passes, also a composition of ops, fusions, more ops. You get the point. All right. So a topic I've been, like a theme that I've noticed like in a lot of discussions like going around the room has been, there's a lot of kernel DSLs out these days. Like there's like, Trident, Qt DSL, Qt Tile, Tilelang, like Mojo, tinygrad, and they're all like pretty darn good. And so, however, like most of the eager ops in PyTorch are written in CUDA, and like most of the compiled ops in PyTorch would be like implemented in Trident via the compiler. So one of our observations was like, hey, like what if it's a lot of effort to like write all of this like permutation. So what if we could get LLMs to like write like all of these like ops to like quickly bring up like a new backend. So the main idea is we created this thing called a backend bench where you can have a directory structure. And in each file in that directory, you can have a specific op implementation. And then at runtime, the dispatcher will like read those op implementations and bind those kernels. So which means that like now if you want to use a custom op, you don't actually need to change user-facing code at all. You'll do something like enable like a flag like backend bench enable, which under the hood will register this op using the PyTorch custom op API. And then you can actually run real numerics tests, and ultimately like a kernel can be fast, it can be correct, but if the numerics don't like really perfectly match eager, it's going to be a hard sell to actually use it in prod. So it's something we wanted to make really first class. You get a score for how many ops you covered and how fast they are. All right. The other thing like we're really thrilled to introduce is Helion. So Helion is like our new take on kernel DSL programming languages. And the reason why it needed to exist is because the vast majority of kernel DSLs today take the trade-off of going lower level to give you more performance over the hardware to squeeze out like that extra bit of performance. We're taking a slightly different bet. So Helion is a higher level language than Trident. It's lower level than PyTorch, so it should be faster. It's also really easy to program and read, and I'll show you an example, and we would posit that this would be true for both humans and LLMs. And kind of like the very big ideological difference is that it's performance portable. Like it's something that we expect to run well, like regardless of the GPU that you pick, whether it's like an A100 or a newer B200, we expect like the performance to be really good. So I'm just going to show you an example of what Helion looks like. So this is a simple matrix multiplication example. You can notice here at the top of it, you have this like Helion decorator. Right below it, you sort of like determine your tensor sizes, and then you allocate like to empty memory. And now the first and only big shift from PyTorch is you have like this new concept of a tile. So really, Helion is PyTorch with tiles. If you have tiles, you can do like these. You can do smaller matrix multiplications over these tiles, accumulate them, get the result, and get like something like really fast and close to the speed of light. So this is great, but like if it's higher level, how can it be faster? Well, the main trick is that, like, okay, yeah, so first off, it's, if you know Helion, you're like, if you know Trident, you already know Helion. The lines of code differences here are like quite dramatic. Like for instance, if you look at like a typical, like for example, like an attention variant, like in Helion, we would expect this to take around like 30 lines of code. And Trident, maybe 120 if you borrow the examples from the docs. And of course, if you're writing like raw CUDA, you'd expect this to be in like 1,000+ lines. So again, it's meant to have the sort of like nice user experience that PyTorch had. Right? But the main trick and the reason how we get performance is we basically auto-tune everything. So you might have noticed in the previous example, you don't sort of specify what are the sort of specific tile parameters. There's no grid launch parameters. There's no thinking about like, should I use grid pointers or block pointers? So pretty much all these decisions that a user might make while they're iterating over a Trident kernel, you just like auto-tune over them, and you can get a kernel that's really fast. And once you get that fast kernel, you can just like deploy it and like no longer auto-tune. All right. So However, like so far we've talked a lot about Pythonic DSLs, but I also want to talk about like some work that we've been doing to introduce like more like native code, like C++ code within PyTorch. So two tools that have like gained a lot of popularity have been load and line in PyTorch and compile kernel. Both of those work by giving in as an input a C++ or like a CUDA string, and it'll basically take it, create the make files for you, bind it, load it as a custom op, and then it'll just like work if you're using like the compiler. So it's like very good for these like, you know, tactical, for tactically changing an individual kernel, right? So what's kind of nice about this is that because like these op definitions are very well scoped, as in like they have like a sort of specific input and output contract, you can actually make this like a leaderboard, and this is like something we've been playing around a lot with in GPU mode, where we do like a bunch of kernel competitions. So if this is like something you're interested, just like feel free to let me know. All right, so okay. So far we've talked about like more like GPU-like architectures, but let's say you take a list of operators, you throw in like a static memory allocator, and you basically end up with like ExecuTorch, which is our solution to run PyTorch on the edge in mobile devices. So I'm like super happy that like ExecuTorch like is now at its like 1.0 GA. The core experience works by you write your Python model, like your PyTorch model, locally on your GPU. You export it, and then once you export it, you can take this binary and load it in the ExecuTorch runtime. And we have like a whole bunch of like different backends here, both that are production ready and alpha ready. So if you're like interested, just like please take a look. And so far, like it's been really nice to see more companies like adopt PyTorch at the edge. So this includes like Facebook's like family of apps, like basically Facebook.com, like WhatsApp, Instagram, but also like our hardware devices where like latency is really key, and a bunch of startups that we've been like really thrilled to collaborate with, like Liquid, Private Mind, and Nimble Edge. And hey, if you're interested in ExecuTorch and want to play around with it and try to see what it's like exporting your models, we have a whole bunch of integrations and people's favorite open source libraries, ranging from like React Native ExecuTorch, like Hugging Face, Torch.io, Unsloth, Ultralytics, and more. Right. So to really iterate, 2025 was a special year for us because like we had like 5 new launches, right? And so just to sort of quickly re-summarize everything. So number 1 is Monarch, which was our solution for having a PyTorch single controller and orchestration. It makes it like really a joy to debug distributed programs and run them in a fault-tolerant way. We have Forge, which is our solution for running large-scale PyTorch native reinforcement learning. We have Torch Comms, which is our new API for running like modern comms in PyTorch. Helion, which is a new kernel DSL that's higher level than PyTorch. Lower level than PyTorch, higher level than Trident. And then, of course, like ExecuTorch 6GA to run PyTorch at the edge, right? So, all right, TLDR, right? So the TLDR is that, our vision was to really have like PyTorch be sort of like an open language of AI that everyone can use. And to sort of like achieve this dream, there's like a few sort of important themes. Like the first is that we really need to make sure that PyTorch is scalable. So we've built like a few technologies here ranging from like dtensor, Monarch, symmetric memory, Torch Titan, and simple FSTP. We need PyTorch to be fast out of the box. So that's why we have technologies like Torch Compile. That's why the partnership with VLM has been really key for us. But we also want PyTorch to be even faster for advanced users that know what they're doing. So that's why we have things like the compiler toolkit and Helion. We want it to run everywhere, which is why like we've developed like Private Use 1, the new Torch Accelerator namespace, and ExecuTorch. And we also really want like a return to form, like basically returning to our roots of the thing that people love the most about PyTorch is that it's like hackable. And to make this possible, we've done a lot of work in making sure like our numerics are rock solid, custom op, backend bench, and tensor subclasses. All right, so it's been, I've been working on PyTorch for 5 years, but PyTorch's been around for 9 years, so thank you for humoring us for these very long 9 years. And we hope you'll stick around for just a bit longer, and thank you.